You have likely experienced this before. You scrub and rinse, expecting a completely clean finish, but instead, you are left with a dull, slightly sticky film clinging to the fabric or your skin. Today, we are going to run a simple 4-step test to isolate exactly what this substance is and where it comes from. To do this, we need a controlled setup. Grab 2 clean, empty glass test tubes, a standard liquid soap solution, and a basic glass dropper. The crucial part of this test relies on our primary variables. We need 2 entirely different types of water. For our control sample, we require exactly 10 milliliters of pure distilled water. If you don't have distilled water available, freshly collected rainwater works perfectly as an alternative. For the test sample, we need another 10 milliliters, but this time it must be hard water. You can usually source this directly from a household tub well or a hand pump. By placing these specific samples side by side, we eliminate the guesswork. We will be able to see clearly whether the soap itself is leaving the residue or if the water is the true cause. Step 1. Carefully measure your 2 10-milliliter water samples and pour them into their respective glass test tubes. Since both liquids look perfectly clear to the naked eye, you must label the tubes distilled and hard right now to avoid losing track of the samples. Step 2. Take your liquid soap solution and add exactly 2 drops into both the distilled water tube and the hard water tube. When you add the soap, ensure your dropper is held completely vertical. Tilting it can create irregular, elongated drops, and we need the volume of soap in both tubes to be perfectly equal. Step 3. Securely cover the tops of both tubes and begin shaking them vigorously at the exact same time. Agitation is what forces the soap and water to interact. The shaking time must be identical for both tubes to keep the physical testing variables absolutely consistent. We will shake them for 10 seconds. 10, 9, 8, keep the pace steady. 3, 2, 1, stop. By standardizing the water volume, the soap quantity, and the shaking time, we have removed any physical inconsistencies from the test. Any visual difference we see now is the result of pure chemistry. Step 4. Place both test tubes down side by side on your table and observe the immediate results. In the tube labeled distilled, you will see what we typically expect from soap: an abundant, thick layer of lather at the top and clear liquid underneath with 0 solid particles. Now look at the hard water tube. It produces almost 0 foam. Instead, the liquid turns cloudy, filled with thick, white, curdy clumps. That newly formed white precipitate floating in the tube has a common household name: soap scum. To understand why this forms in one tube but not the other, we have to look past the visible water and examine what is happening hidden deep inside the hard water sample. This diagram shows the exact composition of our hard water sample. Hard water is defined by containing high concentrations of dissolved minerals, specifically calcium and magnesium ions. Standard liquid soap is formulated using the sodium salts of fatty acids. When you drop soap into the hard water, those sodium salts enter the liquid and physically encounter the dissolved minerals. Look at this chemical equation detailing that exact interaction. As the soap molecules, the 2RCOONA, make physical contact with the calcium chloride in the hard water, a rapid reaction takes place. The soap chemically binds directly to the calcium and magnesium. This combination forms an entirely new compound, an insoluble salt. The dissolved minerals effectively destroy the soap. Instead of creating a lather to clean dirt, the soap's potential is completely wasted, converted into a heavy, useless solid. You have just successfully isolated and visualized a chemical soap scum reaction in a controlled environment. The insoluble salt sinking to the bottom of your test tube is the exact same substance that creates that stubborn, chalky film on your shower tiles, on your clothing, and your skin. Washing with traditional soap in a hard water environment is highly inefficient. A large portion of the product is simply converted into debris before it can clean anything. To bypass this reaction entirely, modern synthetic detergents are necessary. They are specifically formulated to prevent their active molecules from binding with calcium and magnesium ions. By understanding the unseen chemistry of your water supply, you can stop wasting product and choose the correct tools for an effective clean.